Hello there, and welcome. I am the sleepy astronaut. I'm so glad you found your way here. Maybe you have had a rough, draining day, or maybe you just love learning about space and time. Either way, tonight's journey is for you. This evening, we will be traveling to a distant star system known as Trappist-1, a place where 7 Earth-sized worlds orbit a tiny, dim sun, and where the possibility of life lingers in the dark. I am coming right down to Earth to pick you up. I brought along an extra pair of my special faster-than-light boots, just for you. Tonight, we are traveling far from home, 40 light-years away, to a small, cool star that may hold more habitable worlds than any system we have ever discovered. We will visit each of its 7 planets, one by one, drifting through the dark to explore a place where the sky is always twilight, where the sun never sets, and where the possibility of life may be written across entire worlds. It is a long, quiet flight through the dark, designed to let your mind wander and your body sink into rest. If you enjoy these calm journeys through space, I invite you to subscribe or leave a thought below. It helps other astronauts find their way here. But for now, your day on Earth has come to an end, and your journey through the stars has begun. You don't need to do anything. Just relax and let your body sink. Let your eyes grow heavy and allow your mind to drift into space. Let's take off. We leave Earth behind, drifting outward through the quiet dark. The sun grows smaller behind us, a bright, steady star fading into the tapestry of the galaxy. We pass the moon, silent and grey, and leave it to its slow orbit. We cross the orbit of Mars, then Jupiter, then the distant, frozen edge of our solar system. We pass beyond the Kuiper belt, beyond the heliopause, and into the interstellar void. 40 light-years is a long journey. Light itself takes 4 decades to cross the gap we are traveling. But in our faster-than-light boots, the journey passes like a dream. The stars drift past us, slow and silent, and we let our minds wander through the dark. We pass by familiar constellations, Orion, with its hunter's belt, slowly fading behind us. We glide past the Pleiades, that cluster of young, hot stars shimmering in the distance. We are leaving our cosmic neighborhood behind, traveling into the vast, quiet unknown. We have been traveling for what feels like hours, drifting through the endless dark, when a faint, reddish glow begins to emerge ahead of us. It is not a brilliant beacon like our sun. It is small, cool, and dim, barely a candle flame in the vast ocean of space. This is Trappist-1, an ultra-cool dwarf star, only about 8% the mass of our sun. It is so small that if you placed it in our solar system, its edge would barely extend beyond the orbit of Jupiter. It is a quiet star, a patient ember in the dark, slowly burning its fuel over trillions of years. Unlike our sun, which will burn for about 10 billion years before dying, this tiny star will continue to glow for 100 trillion years or more. A quiet light in the dark long after our own sun has faded away. The star is relatively old, at least 500 million years older than our sun, which means that any life that might have arisen on its worlds has had plenty of time to evolve. It is also a very quiet star for its type. Many red dwarfs are prone to violent flares that could strip away the atmospheres of nearby planets. Trappist-1 is relatively calm, making it a more promising candidate for habitability. The star has a mass of about 80% of Earth's mass, and its radius is about 12% of our Sun's. Its surface temperature is about 2,300 degrees Kelvin, compared to about 5,800 degrees Kelvin for the Sun. It is a dim, cool star, a gentle ember in the vast, dark sky. The discovery of Trappist-1 was announced in 2017, and it sent ripples of excitement through the scientific community. It was discovered by the Trappist telescope, a small robotic telescope located in the Chilean desert, designed to hunt for exoplanets orbiting nearby stars. The telescope's name stands for Transiting Planets and Planetesimals Small Telescope, and it was operated by astronomers from the University of Liège in Belgium. They were observing a small, unassuming red dwarf star when they noticed something extraordinary. Faint, regular dips in its light, indicating that something was passing in front of it. Those dips were planets, not just one or two, but seven. 7 Earth-sized worlds, all huddled close to their parent star, all transiting its face in a rhythmic, almost musical pattern. The astronomers were stunned. Never before had they found a system with 7 Earth-sized planets, let alone 3 in the habitable zone. It was a discovery that would change our understanding of planetary systems forever. The Trappist telescope was not a large instrument. It was less than 2 feet across, comparable to a backyard telescope. But it was equipped with sensitive cameras and placed in one of the darkest, clearest skies on Earth. It watched Trappist-1 for hundreds of hours, patiently recording its light and waiting for the telltale dips. Over time, the pattern emerged, a symphony of transits, each one revealing a different world. The discovery was confirmed by other telescopes, including the Spitzer Space Telescope, which provided additional observations of the system. Spitzer was an infrared telescope, launched in 2003, and it operated for over 16 years before being retired. Its infrared eyes could see through the dust and gas that sometimes obscures visible light, making it the perfect instrument for studying the Trappist-1 system. It was Spitzer that confirmed the 7th planet, completing the family portrait of this remarkable system. The discovery of Trappist-1 was announced at a press conference in Washington, D.C., and it quickly became one of the most talked about stories in the world of space exploration. The headlines read, 7 Earth-sized worlds found orbiting a nearby star, and the search for life just got much more interesting. Scientists were excited, but they also knew that much more work needed to be done. The James Webb Space Telescope, the successor to Hubble, was preparing for launch, and it would be able to study the atmospheres of these worlds in detail, looking for water, oxygen, methane, and other signs of life. It would take years to fully understand the Trappist-1 system, but the discovery was a giant leap forward. The discovery of Trappist-1 was a turning point in exoplanet research. It demonstrated that planetary systems can be vastly different from our own, and that Earth-sized planets in the habitable zone are not as rare as some scientists had feared. It also showed the power of small, dedicated telescopes to make groundbreaking discoveries. The Trappist telescope, along with its sister instrument in Morocco, has continued to search for exoplanets and has found many more systems, but none have been quite like Trappist-1, with its 7 worlds so tightly packed and so similar to our own. Now, Let us consider the star itself in greater detail. Trappist-1 is a red dwarf, a class of star that is the most common in the universe. They are small, cool, and long-lived, burning their fuel slowly over trillions of years. They are also notoriously difficult to observe because they are so dim. But they are incredibly interesting from a habitability perspective. Because they are so small, planets can orbit very close to them and still be in the habitable zone. This means that red dwarfs could potentially have more habitable worlds than larger stars like our Sun. However, there are also challenges for life around red dwarfs. The habitable zone is very close to the star, which means that planets are likely to be tidally locked, with one side always facing the star. This could lead to extreme temperature differences, with the day side being too hot and the night side too cold. The terminator zone, the boundary between day and night, could be the only place where liquid water could exist. Additionally, red dwarfs can be prone to flares, which could strip away the atmospheres of nearby planets. Trappist-1 is relatively calm for a red dwarf, which makes it a more promising candidate for life. The Trappist-1 system is also located in a relatively quiet part of the galaxy. It is not near any dangerous radiation sources or other stars that could disrupt its planet's orbits. This stability has likely contributed to the system's longevity and the potential for life to arise. The star's position in the galaxy is also important for astronomical observations. It is relatively close to Earth, at only 40 light-years away, making it a prime target for study. 7 planets orbit Trappist-1. 7 worlds, all roughly the size of Earth, all huddled close to their parent star in a space smaller than the orbit of Mercury. If you were to place the Trappist-1 system inside our own solar system, all 7 planets would fit within the orbit of Mercury. They are so close together that from the surface of one, you could look up and see the others hanging in the sky like distant moons, larger and brighter than our own moon appears to us. Imagine looking up at the night sky and seeing not one but several Earth-sized worlds, each one glowing with its own dim, reddish light, each one a world of its own. It is a system of impossible intimacy, a tightly packed family of worlds, held in the gentle grip of a tiny, distant sun. They are bathed in a perpetual twilight, their skies painted in shades of deep red and orange, their surfaces wrapped in the dim, warm glow of a star that will never know night. The sun on Trappist-1 would appear far larger in the sky than our sun does, because the planets orbit so close to it. But it would be dimmer, a deep orange-red disk that casts a soft, warm light over the landscape. There would be no bright, harsh glare, no shadows that cut sharply across the ground. Everything would be bathed in a perpetual, soft twilight, a world of gentle contrasts and muted colors. 3 of these planets orbit within the habitable zone, where temperatures could allow liquid water to exist on their surfaces. 3 worlds with the potential for oceans, for life, for maybe something more. And the other 4 orbit nearby, close enough that their fate may be linked to their siblings in ways we are only beginning to understand. The planets are all tidally locked, meaning that one side always faces the star, and the other is in permanent darkness. This creates a stark contrast between the day side and the night side, with possible ice formation on the dark side and warmer temperatures on the light side. The boundary between the two known as the Terminator, could be a zone of moderate temperatures where life could potentially thrive. Let us visit them now, one by one. We approach the first of these worlds. It is called Trappist-1b, the closest to its star. It is a rocky world, roughly the same size as Earth, but its orbit is tight and swift. It circles its dim sun in just a day and a half, racing through the dark in a desperate, hurried path. The surface of this world is likely hot, its day side bathed in the constant glow of its parent star, its night side frozen in eternal shadow. It is a world of extremes, caught in the grip of a star that never sets. Its orbit is so close that it may be tidally locked, meaning one side always faces the star, forever bathed in its dim, red light, while the other side is forever dark. The temperature on the day side may be hundreds of degrees Celsius, hot enough to melt lead, while the night side may be frozen solid. It is a world of stark contrast, a place of fire and ice caught in the relentless embrace of its star. The atmosphere, if it has one, would likely be stripped away by the intense radiation of the star, leaving behind a barren, airless surface. Its surface would be covered in craters and volcanic flows, a harsh and unforgiving landscape. Yet even in its extremity, there is a kind of beauty to it, a stark and silent world racing through the dark. We drift past Trappist-1b, leaving it to its swift, relentless orbit, and continue our journey. The next world is Trappist-1c. It is similar in size to its neighbor, but its orbit is slightly wider, taking about 2.5 days to complete a single revolution. It receives only a little less light than its sibling, and its surface may be similarly extreme. Scientists believe that both of these inner worlds may have atmospheres that have been stripped away by the intense radiation of their young star, leaving behind barren, airless surfaces. They are worlds of stone and shadow, silent and stark, their surfaces scarred by billions of years of solar wind and radiation. Yet, even in their barrenness, they hold clues to the formation of the system, to the violent, chaotic processes that shape these 7 worlds. Their surfaces may be covered in ancient craters, preserving the history of the early solar system. We drift past them, imagining their silent, stark landscapes, and continue deeper into the system. Now, we approach the first of the worlds that lies within the habitable zone. Trappist-1d is the smallest of the 7 planets, about 3/4 the size of Earth. It orbits at a distance where water could potentially exist on its surface, if its atmosphere is thick enough to retain warmth. It is a world of possibility, a quiet, patient place, waiting for the conditions to be right. We do not know if it has water, or if it has ever had water, but it is there, drifting in the dark, a world that might hold the secret of life. Its orbit takes about 4 days, and it receives about the same amount of energy from its star as Mars receives from our Sun. It may be a cold, dry world, its surface frozen and barren, or it may have a thick atmosphere that traps heat and allows liquid water to exist. The ice on its surface could be kilometers thick, covering a dark, frozen ocean. Or the ice could be thin with liquid water beneath it, kept warm by geothermal activity. We drift past it, leaving it to its patient silence, and continue our journey. We have visited 3 worlds so far. 3 more lie ahead, including the most promising of all, Trappist-1e. But that is for the next part of our journey. For now, Let us pause. Let us rest here, in the quiet dark of the Trappist-1 system, and feel the weight of what we have seen. A star, small and dim, surrounded by a family of worlds. A discovery that changed our understanding of the universe. A system full of possibility. When you are ready, we will drift further. But there is no rush. We have rested long enough. Now, take my hand again. There are more worlds to visit, more wonders to drift past in the quiet dark. The fourth world we approach is Trappist-1e, the most promising of all. It is the same size as Earth, and it orbits at a distance that is almost exactly the same distance from its star as Earth is from ours. It is the Goldilocks world of the Trappist system, not too hot, not too cold. It receives the same amount of light as Earth, but the light is different. It is red, dim, and cool. A perpetual twilight that would make our own sunset seem bright by comparison. The sky on Trappist-1e would always be the color of our twilight, a warm, reddish glow that never fades. This is the world that astrobiologists dream of. Trappist-1e is considered the most Earth-like of all the known exoplanets. Its radius is about 1.05 times that of Earth, and its mass is roughly 9/10 of Earth's mass, making it one of the most similar worlds to our own ever discovered. It orbits its star at a distance of about 6.5 million kilometers, which is only about 4% of the distance between Earth and the Sun. Because its star is so much dimmer than ours, this close orbit still places it firmly in the habitable zone, where liquid water could exist on its surface. Its year is only 6.1 Earth days long. If you lived on Trappist-1e, you would celebrate a birthday every week, and the seasons would be determined not by axial tilt, but by the subtle variations in the star's activity. The gravity on Trappist-1e is likely similar to Earth's, given its mass and radius. It has a density comparable to Earth's, suggesting a rocky composition with a metallic core. It is thought to be a terrestrial planet like our own, with a surface of rock and metal. It has a thin atmosphere, or maybe a thick one. We do not know. But it is there, drifting in the dark, a world of possibility waiting to reveal its secrets. The James Webb Space Telescope has already begun studying its atmosphere, looking for signs of water, carbon dioxide, methane, and other molecules that could indicate the presence of life. The observations are ongoing, and the results are eagerly awaited. Let us pause here, traveler. Let us touch down gently on this distant world. We descend through an atmosphere, perhaps thin, perhaps thick. We cannot know yet, but let us imagine. The surface beneath our feet is rocky and ancient, carved by wind and water over billions of years. In the distance, a deep, dark ocean shimmers under the dim red light of its parent star. The waves lap gently against a rocky shore, and the sky above is a soft, reddish-purple glow. The sun a small, dark disk on the horizon, surrounded by a halo of fiery light. The temperature is cool but not cold, like a spring evening on Earth, with a gentle breeze that carries the faint scent of salt and something else, something unknown. We stand there, in the quiet dark, and we wonder, what might live in those waters? Perhaps nothing yet. Perhaps the planet is silent, waiting. The chemical building blocks of life may be there: carbon, hydrogen, nitrogen, oxygen, phosphorus. But they have not yet assembled themselves into the first fragile spark of life. The waters are sterile. The land is empty. The planet is a womb, ready but unseeded. It has been waiting for billions of years, and it will wait for billions more. Life is not inevitable. It is a rare and precious thing, and it may be that this world, so similar to our own, remains silent forever. Or perhaps something does swim in those depths. Microorganisms, simple and ancient, drifting through the currents, like the earliest life on Earth. Single-celled creatures, patient and endless, feeding on the minerals that seep from volcanic vents at the bottom of the sea. They do not think. They do not feel. They simply are. A silent, invisible civilization of tiny beings, the first stirrings of something greater. Their world is dark and warm, lit only by the faint glow of hydrothermal vents and the distant, dim light of their star. They have existed for eons, unchanged, their evolution frozen in the deep, still waters of their ocean. And perhaps in time, if we could wait millions of years, those microorganisms would evolve. They would grow more complex, more curious. They might develop fins, then limbs, then eyes that gaze up through the dark water at the dim red star above. They might crawl onto land, breathe the thin air, and one day look up and wonder what lies beyond their sky. Perhaps if we wait long enough, they would build their own ships, their own telescopes, their own dreams of exploring the unknown. They would wonder if they are alone in the universe, and they would never know that we were here, watching them from across the void. Their entire civilization, their rise and fall, their dreams and achievements would unfold in a blink of cosmic time, and we would have seen it all from our quiet perch among the stars. They would have their own myths and legends, their own science and philosophy. They would look up at the dim red star and wonder why it is the way it is. They would study the other worlds in their system and dream of visiting them. And one day, perhaps, they would succeed. But we cannot wait that long. We have journeys to continue. So we lift off gently from Trappist-1e, rising back into the silent void. Below us, the red world grows smaller, fading into the darkness. We carry with us the thought of its hidden oceans, its maybe life, its silent possibility. It is a thought that lingers, a gentle echo in our minds, like the memory of a dream. We drift onward, passing Trappist-1f. This world is slightly larger than Earth, with a radius about 1.05 times that of Earth, and it orbits at the outer edge of the habitable zone. It takes about 9.2 days to complete one orbit around its star. It receives less light than its sibling, and its surface may be covered in ice, or it may have a thick atmosphere that traps heat and allows liquid water to exist. Its mass is estimated to be about 1.5 times that of Earth, suggesting a composition rich in ices or water. It may be a water world, with deep global oceans and no exposed land. The pressure at the bottom of those oceans could be immense, crushing anything that dared to descend. We drift past it, leaving it to its frozen mystery, and continue onward. Next is Trappist-1g, a world larger than Earth, with a radius about 1.2 times that of Earth, orbiting just beyond its sibling. It takes about 12.3 days to complete one orbit around its star. It may have an atmosphere thick enough to support life, or it may be a frozen world, locked in an eternal winter. Its surface, if it is frozen, would be a landscape of ice and rock, bathed in the dim red glow of a distant sun. It is a world of shadows, its day a perpetual twilight, its night a deep, star-studded dark. Its mass is about 1.5 times that of Earth, and its density is similar to Earth's, suggesting a rocky composition. We drift past it, imagining the silence of its frozen plains, and continue our journey. Finally, Trappist-1H, the outermost world. It is smaller than Earth, with a radius about 3/4 of Earth's, and it orbits at the edge of the system where the light of its parent star is faint and distant. It takes about 20 days to complete one orbit around its star. It is likely a frozen world, its surface a barren, icy wasteland, its atmosphere thin and tenuous. It is the quiet sibling of this family, a distant outpost in the dark. Its mass is estimated to be about 1/3 of Earth's mass, suggesting a composition rich in ices. It is a world of cold and shadow, of silent, endless winter. We drift past it, leaving it to its frozen solitude. We have traveled through the Trappist-1 system, past 7 worlds, each one a world of its own, each one a story of its own. Some of them may have water, some may have atmospheres, some may have life. We do not know, but we have imagined them, and that is enough. Now, let us reflect on how rare this system truly is. In the vast, silent expanse of the galaxy, there are billions of stars and billions more planets. But systems like Trappist-1 are thought to be remarkably rare. Most stars do not have 7 Earth-sized planets, let alone 3 in the habitable zone. The discovery of this system was a stroke of luck, a glimpse into a kind of planetary architecture that we had never seen before. It challenges our understanding of how planets form and evolve, and it raises the possibility that other such systems might exist, waiting to be discovered. The rarity of the Trappist-1 system is not just about the number of planets. It is also about their configuration. The planets are in a resonant chain, meaning their orbits are synchronized in a precise mathematical relationship. For every orbit of the innermost planet, the next one completes a certain number of orbits, and so on. This resonance is not accidental. It suggests that the system has been stable for billions of years, and that the planets have gradually settled into their current orbits over time. The resonance also helps to keep the system stable, preventing the planets from crashing into each other or being ejected from the system. It is a testament to the delicate balance of the cosmos. The Trappist-1 system is also rare because of the star itself. Ultra-cool dwarf stars like Trappist-1 are the most common type of star in the galaxy, but they are difficult to study because they are so dim. The Trappist telescope was specifically designed to find planets around these small stars, and it succeeded beyond anyone's expectations. Without the Trappist project, we might never have known about this remarkable system. It is a reminder that sometimes the greatest discoveries come from the smallest, most patient instruments. Now, let us consider what life might be like on these worlds. If there is life on Trappist-1e, what would it look like? The dim, red light of its star would have a profound effect on the evolution of any life that exists there. Photosynthesis would be different, with organisms evolving to use the longer wavelengths of light. The plants would be dark, perhaps black or deep purple, absorbing as much light as possible. The animals would have eyes adapted to the dim light, perhaps with larger pupils or different types of photoreceptors. The sky would always be a deep reddish orange, and the stars would be visible even during the day. The environment would be quiet, the wind gentle, the colors muted. It would be a world of subtle beauty, a place where the boundaries between day and night are soft and blurred. The deep red light of Trappist-1 would cast long, soft shadows, and the colors of the world would be muted and warm. The plants, if they exist, would need to be extremely efficient at photosynthesis, perhaps using chlorophyll-like molecules that absorb red light. The animals would have eyes that are sensitive to the dim light, and they would likely have adapted to the perpetual twilight. The soundscape might be dominated by the wind, the waves, and the calls of unknown creatures. It would be a world of quiet, simple beauty, a place that feels like a gentle, eternal dusk. If humans had evolved on Trappist-1e instead of Earth, our entire experience of the world would be different. We would have evolved in perpetual twilight, our sleep-wake cycles synchronized to the slow rotation of our planet. We would have never known true darkness, nor the harsh glare of a bright sun. Our culture, our art, our science would be shaped by this environment. Our literature would be filled with stories of the dark side of the planet, the forbidden lands of perpetual night. Our explorers would dream of crossing the Terminator, of seeing the stars in their full glory. Our civilization would have unfolded under a dim, red sky, and our understanding of the universe would be shaped by the view we had of it. Our language would have words for shades of red that we cannot even imagine. Our poetry would be filled with images of the constant twilight, the eternal sunset. Our science would have developed differently, driven by the need to understand a world where there are no sharp shadows, no bright days or dark nights. Our technology would have adapted to the low light, with different types of sensors and imaging techniques. And when we finally reached for the stars, we would have a unique perspective on the universe, shaped by our home world and its place in the Trappist-1 system. And what about the future of the Trappist-1 system? If there is life there, what will become of it? The star will continue to burn for trillions of years, far longer than our sun. This means that life, if it exists, has an extraordinarily long time to evolve. It could develop intelligence, technology, civilization. It could spread from one world to another, colonizing the 6 other planets in the system. The planets are so close together that they are almost within reach of each other. With a modest amount of technology, a civilization on one world could easily travel to the next. They could build a solar system-wide civilization, with each planet serving a different purpose. The inner worlds could be industrial centers, the middle worlds agricultural, the outer worlds research colonies. They would have a unique perspective on the universe, living in a system with 7 habitable worlds, all within reach. They would see their own world and its neighbors as a single interconnected system, a family of worlds, bound together by gravity and shared destiny. And perhaps one day, they would look up at the sky and see the stars beyond their system. They would wonder what lies out there in the vast, dark expanse of the galaxy. They would